nucleus, why would it be kind of naturally pushing apart or trying to separate?
Because the protons all have the same charge if they're repelled.
Good. So the positive and positive would typically want to push away from each other. And because of that, this is probably where we left off. You should have slide number 8 done, I think.
Whenever like the protons break off, where do those go?
Okay, so what they do is they will decay into another, like they don't disappear. What they do is now, like this group has a certain number of protons and this group has a new number of protons, and so they basically decay into a smaller element. So like if they had
go into another atom or something?
No, they actually form a new one. So just like that video showed, like it breaks down into, because remember, you identify the element by however many protons it has. So if you started with 30 protons and then it broke off into like 15 and 15, they would turn into whatever atom is atomic number 15, which I don't know right off the top of my head. So yeah, it would turn into like phosphorus. Right? So if it started at atomic number of 30 for zinc and it broke down into 2 different atoms that each had 15 protons, you'd end up with 2 phosphoruses, which that's not a really good example because those are not actually, like that wouldn't actually happen because those nuclei aren't big enough. But that's what happens. The protons don't disappear and they don't change into anything else. What they do is now you have 2 new elements that have formed, and we'll take a look at some of these examples and you'll kind of see, but that's a good question. I don't want you to think that the protons change. The protons themselves stay the same, it's just how many of those protons do you now have, and if you change number of protons, you change the element you're dealing with. Okay, so typically when you have a really large nucleus, that's when you can run into some trouble, because we said that there was this strong attractive force that keeps the nucleus together normally, and it's able to do this because it's small enough, like you see here, where there's enough attraction throughout the entire nucleus that it's able to stay together. But if the nucleus is too big, you get like pockets of attraction, so like this is all attracted, but it's not really attracting to anything over here. And that's when the decay process can happen. Okay, and so we'll take a look. I have a couple examples that'll show this. So this is our first slide for today. So real quick, what are the 2 particles that you find in the nucleus? What are those 2 subatomic particles?
Protons and neutrons.
Good. All right, so our protons and neutrons are out there. And again, what charge do the protons have? Stop it. What charge? Thank you, Audrey. I see the sign. Okay, good. We have that positive. So what overall charge does the nucleus have? If that's where the protons are found.
None.
What?
None.
None?
Charge.
Well, if the protons are there, right, the neutrons have no charge, but the nucleus itself has the protons and the neutrons. So if the protons are positive, kind of by default, Audrey's showing me a plus sign. Were you thinking neutrons?
I was thinking, yeah.
Yeah. So just be careful, because the neutron and the nucleus, both those words look so similar. Be careful that you're sure what the question is asking. Okay, but because the protons are in the nucleus, that makes it positive. And then this is what I said I didn't really like. It's kind of a generic term, and it's that strong nuclear force or that attractive nuclear force. You'll hear it kind of called both ways. So it's kind of describing what's happening. It's like a description of the force holding it together. So if you have a really, really, really big nucleus, or the plural form of nucleus, nuclei, is the attractive force strong enough to hold it all together? What do you guys think? I see some yeses, I see some nos. Sometimes yes, sometimes no, but not usually. Usually if it's too big, that's when the decay process will happen. So it's going to be usually atoms that are, have an atomic number of like 80, 90, pretty high, right? and so usually it's because they're just too big. They can't keep it all together, right? It's not able to have that attraction strong enough throughout the entire atom. Like I said, it'll hold like this part of it, and maybe this part of it, and this part of it, but to hold all of it together at once, it's too big. And so if you think of like a crowd of people, if we have like 5 people that are being kind of rowdy, you can kind of keep them under control. You can keep that contained. If you have 5,000 people who are rowdy, you have a lot less chance of keeping them under control. And not that I'm saying like an atom is rowdy or a nucleus is being rowdy, but you know, if you think of that example, if you have like 5 little kids that are running around in crazy hyper, okay, like 5 you could probably manage, but 5,000, can't keep them contained.
You can't even manage 5 kids.
I know, I personally wouldn't want to try. Well, you'd have a much better chance at least than if you had 5,000. Okay, so we are going to move into radioactivity. All right, and so this is one of our first 3 main topics for this unit, and there's still some review involved in this. But we're going to take this idea of the strong attractive nuclear force, understanding that that usually keeps the nucleus together. The neutrons kind of act as that atomic glue. The neutrons kind of neutralize that repulsion that the protons would typically feel. And so we know that that's why most atoms are not radioactive, and most of them are very stable, and they're going to stay the way they are. Problem is, when the nucleus, or when the attractive force is not able to keep it together, some things happen. The nucleus starts to decay, and when I say decay, I don't mean like rot. It's not like a dead animal on the side of the road decomposing, okay? When we say decay and we're talking like chemistry, we're talking like the breakdown, okay? And so this nucleus is gonna break down into something smaller. But when this happens, this gives off a lot of energy, and this is known as radioactivity. This can technically happen in large or small nuclei. This can happen with carbon. There's an isotope for carbon that we actually talked about last year. There's some other small nuclei that do have isotopes that are typically and commonly found. But most of the time, this is going to happen with really, really, really large nuclei. So sometimes if you have a large nuclei and you get a catalyst, which is like something that will trigger a reaction, you can get that decay process to start. And we'll talk about this in a little bit later on this week. Okay. But usually it's the large nuclei kind of on their own that they are just not able to fight that repulsion of the protons, and they start pushing apart. And when that happens, they will decay into smaller elements, because now you have different numbers of protons, right? So if you started with 80 protons, and then you break down and one has 60 and one has 20, you have 2 new elements. Whichever element has an atomic number of 60 and the other element that has an atomic number of 20, now you have 2 new elements from that original element. Okay, so again, you're going to hear this word decay used a lot. And again, don't think of it as rotting. All that's really happening is that the nucleus is rearranging. And again, it's trying to do this to get stable, because as the protons start to repel, like that, the attractive nuclear force and the neutrons can't neutralize that repulsion anymore, and the protons are like, oh, we're gonna break apart, and they separate. They're just going to separate into new atoms. They're just rearranging. So it's not like you're deleting protons. All that's happening is they're shifting into a new element. And so the rearranging means the number of neutrons and the number of protons are changing, giving you a new element since the protons changed. So this is the first time we've looked at really protons being affected. We looked at, electrons changing, we've looked at neutrons changing, but when this decay process happens, we change the number of protons, but by default, we're also changing the element that we're dealing with. Because we've changed the number of neutrons, or excuse me, changed the number of protons. Okay, so most of the time this is gonna happen with atoms that have an atomic number of 84 or higher. You have 84 protons. All of those repulsion, those normal repelling forces that would be at work to push away from each other. You have 84 of them in every direction, right? Like, and you have these neutrons trying to hold it all together, right? So it just keeps, when it gets so big, the protons kind of start to win, right? The nuclei is too large and the neutrons cannot counteract that normal repelling behavior of the protons. And that's when the decay process will happen. When we get to about 93 for an atomic number, these elements typically don't last very long in nature because they're going to decay and break down so quickly. Anything bigger than 93, it's a thing, like it does exist, but typically it's not going to last long on its own. It's going to start breaking down. And these bigger elements we can synthetically produce in labs, and they are unstable and they decay very quickly. It's kind of like the alkali metals, right? They're so reactive chemically because they want so badly to get rid of their one electron so that they can drop down to the next energy level. And it's like the halogens. They're one away from having a full valence. So that's why the halogens and the alkali metals typically are not going to be found in nature on their own because they're going to react so quickly because they are so desperate to get rid of the electron or to gain an electron to get their valence full. So it's kind of the same idea, but we're talking, nuclear reactions here, right? They're trying to get the nucleus stable, not dealing with electrons like we talked about before. Okay, so here's an example, right? And this might kind of help put it all together. You can carry a small stack of boxes, like no problem. Like you can like walk down the hall, like, okay, carry these, I got it, right? Don't even really have to worry about it. This is kind of like a small nucleus. So like our 84 and under. But if you try to carry too many boxes, right, you have them all stacked up, you're kind of like, whoa, and one starts shifting, and the next thing you know, you don't have control of them anymore, and they fall apart. This would be like a really large nucleus. You can only keep it stable for so long. So even if like you start off good, and you're like, okay, and then all of a sudden one in the middle starts to shift a little, and then you're like, whoa, right, trying to keep it all balanced, right? So if you have this really large nucleus, the neutrons can only keep it balanced for so long and overcome that repulsion that the protons would feel, right? And eventually it's going to end up like this and kind of fall apart. So the small stack is like our small nuclei. Large stack of boxes you can only keep stable for so long, like our large nuclei. Another example is like a popcorn ball. Has anybody ever made popcorn balls? Anybody ever eaten them? Okay, so if you have like a normal size popcorn ball, they're about like the size of a softball, between a baseball and a softball probably. And like it's just like the little ball, and you like, you can break off pieces, or you can, eat a bite of it. Usually there's like caramel and peanut butter, and like, it's all nice and gooey and it stays together. Okay, they usually are about this size. Usually you're not going to find really, really, really big ones, right? Reason why is they'd be way too big and they're not sticky enough to keep the whole thing intact. So like if you try to have a giant one like this, it's going to kind of stay together for a little bit, but then like you might have a piece that falls off and then like another piece that falls off. Like it's not sticky enough to keep the entire thing contained, right, and held together. So it's not like it's going to all fall apart and you'll have all the pieces down, right? It's going to fall in clumps. It's going to break apart in these big giant clumps. So you have to keep the popcorn ball pretty small so that it can stay all together. So this is like the nucleus. right? It can stay together when it's small, but when it gets too big, it's going to fall apart or decay. And I know for me, those two examples help. I hope that they help you kind of think of what's going on with the nucleus. Okay, so quick review. Atomic number is our number of protons, and our mass number is our number of protons and neutrons. Remember, mass number is the big one. It's counting those two subatomic particles. And remember, that was in one of those little cloud bubbles at the bottom of your periodic table in my handwriting, right? And so we know that in a neutral atom, protons and electrons are also going to be equal. So we can figure out how many total electrons we have. And again, this is just review from our periodic table unit. So our mass number is our big one, our atomic number is the small one. Here's our atomic symbol for sodium, and then this is actually even showing the charge, which most of the periodic table stuff we looked at hasn't shown the charge on the symbol, but some do. So if I have an atomic number of 11, I know that I have 11 protons, and I know that I would have 11 total electrons as well. Anybody remember how you would find the number of neutrons? Because I see no number for the number of neutrons. Let's see, what do you think, Kate?
The mass minus the atomic number.
Very good, because this is protons and neutrons. Subtracting protons will leave you with just your number of neutrons. Good. All right, so the atomic number, the number of protons can't change, right? Because if we do change it, we'd have to change the elements. We can change electrons to get our ion version of the element. And we also can change the number of neutrons to get our isotope version. So protons has to stay the same. So carbon has to always have 6 protons. I can change electrons to help get this stable and satisfied. And I can also change the number of neutrons. And those versions are the ion if you change electrons, or it's the isotope if you change neutrons. And again, you guys are getting much better at separating these two out. All right, and so we had this little kind of cheat sheet or way to distinguish between the atomic number and the mass number. And atomic number is going to be the smaller of the two. Right, and I said, hey, think of an atom and how small an atom is. It's going to be the small one. The atomic number is the small one. And then logically, if you think about it, it only has protons. So of course, just counting one subatomic particle is going to be a lot simpler and smaller than if you count both subatomic particles. Right, here we're just counting protons. So the mass number obviously is going to be the larger of the two. It has the word mass, or massive, it has the word mass in it. Massive meaning large. And this one's counting both subatomic particles. So basically you're counting up the nucleus. Right? So counting 2 parts of something is going to give you a bigger number. So if in here I say, okay, I'm only going to count people with blue eyes. Okay, maybe there'd be like 6 or 7 of you. If I say I'm going to count people with blue and brown eyes, well, that's going to be a larger number probably, right? Because I'm counting 2 eye colors, not just one. Okay, so typically counting 2 of something is going to give you a bigger number. Okay, ooh, that's fuzzy. Okay, so isotopes, and this is kind of where our focus is and why we're kind of backtracking and reviewing the parts of the atom again. Isotopes are going to be atoms of the same element with a different number of neutrons. So hydrogen has 3 different versions. Notice how all the hydrogens have 1 proton. That's what makes them hydrogen. But then here, hydrogen 1 means we name the isotope based on the mass number, right? So all you have is 1 subatomic particle. So mass number is 1. I count 1 proton, and then the green are my neutrons. So I'm counting the 2 things that are in the nucleus, so that gives it a mass number of 2. Here for hydrogen, it's still hydrogen because it's 1 proton, but now I have 2 neutrons. So 1, 2, 3, and we name the element based on its mass number. So this is hydrogen 1, hydrogen 2, and hydrogen 3. and I would know how many neutrons it has by subtracting the atomic number of 1 from the mass number. So if I have 1 minus 1, well, then I have 0 neutrons. If I have 1 minus 0, right, we just end up with our mass number of 1. If I have a mass number of 2, and I subtract my protons, I get 2 minus 1, leaving me with 1 neutron. If I take my mass number of 3, subtract it from my atomic number, 3 minus 1 gives me 2 neutrons. So if you take the mass number and you subtract it from another mass number, that's gonna usually give you how many neutrons, or like give you the isotope version of that element. Okay, so we'll take a look at that a little bit more. So if we look at helium, there's 2 typical isotopes that can form. So again, helium always has 2 protons. So here I have the 2 protons, but now I have a mass number of 3. So if I take 3 minus my 2, my atomic number, it leaves me with 1 neutron. Mass number of 4, so I have 1, 2, 3, 4. So if I know that I have a mass number of 4, if I subtract it from my 2 protons, that's telling me this one has 2 neutrons. So again, you can find that number of neutrons, but there's never going to be like a number written on the little tile on the periodic table for those neutrons. Okay. Okay. And then finally, lithium. Again, I know it's lithium because I have 3 protons, and that doesn't change. But what's changing is my number of neutrons. So I have 1, 2, 3, 4, 5, 6, and I call this lithium 6. This one is lithium 7 because it has 1, 2, 3, 4, 5, 6, 7. Right? And so if I take my 7, subtract it from my 3, I know that I end up with 4 neutrons. If I take my 6, subtract it from my 3, then I know I end up with 3 neutrons. Right? So those are the isotope versions of those elements.